everybody, and welcome. Last video on equilibrium. I'm sure we're very excited. Equilibrium is very different from any type of chemistry we have done, but it's exciting because it is so different. This is real chemistry that we've been doing. But anyway, let's wrap this unit up and talk about the common ion effect. So our last video, we talked about the solubility of salts or ionic salts. And we saw that even though we could say that something is relatively insoluble, everything dissolves at least a little bit. And we can identify how much does something dissociate or dissolve by looking at their value for KSP, right? Or the solubility product constant. And we can't really affect the equilibrium for a particular dissociation like this right here. I'm just going to reference this guy. Can't affect that by adding more silver chloride, because more silver chloride is not going to dissociate in a saturated solution that is already at equilibrium. But what I can do is I can force to actually produce more precipitate of silver chloride by adding what's known as a common ion to that particular solution. So the common ion effect lowers the solubility of a salt. So it makes a salt less soluble. So it makes a salt less soluble, which leads to more precipitate. Less soluble means more precipitate. So I could force precipitation by adding a common ion. So it's a way to control solubility and precipitation. And this is an application of Le Chatelier, our favorite. Le Chatelier's principle. Spelling principle wrong here. So the common ion effect is a wonderful application of Le Chatelier's principle because it can increase the concentration of one of the ions, and because they are aqueous, I'm changing that concentration. They do affect the equilibrium and whether or not it favors reactant or products. So if I take a look at this one right here, my silver chloride is in equilibrium with silver ions and chloride ions. I can make more silver chloride by increasing either the concentration of silver ions or the concentration of chloride ions. And I can increase these concentrations by adding another solution that contains these ions already dissolved. So I can't add more silver chloride and expect that to dissolve to raise the concentration because it's already maxed out. I have to add another solution that contains those ions in it. So if I add something, so for example, I can promote precipitation of silver chloride by adding some sodium chloride solution. Either the sodium chloride salt is going to dissociate, which then increases my concentration of chloride ions, which would force the reaction to go towards the reverse, in the reverse direction. I can produce more silver chloride if I add salt or if I add a solution that has chloride ions already dissolved in it. So for example, let's say I have this solution right here. So I have a silver chloride solution, and this has to be saturated because I have that solid material sitting at the bottom, right? That's what makes a solution saturated, because the rate at which this solute is dissolving is equal to the rate at which it recrystallizes back onto that solid silver chloride at the bottom. But if I have a salt solution and I add some silver chloride to that, I'm adding this silver chloride to a solution that already has a lot of chloride ions. So because there's a very high concentration of chloride ions to begin with, I can produce even more silver chloride solid. So that's what this is showing. This is a lot of solid silver chloride. I can make more of that because I have that higher concentration of one of those aqueous products. And this is the whole idea behind the common ion effect. I'm using the fact that an equilibrium is affected by a change in concentration. I'm also using Le Chatelier's principle to show that there's a shift in one direction. It favors precipitation. We have a lot of different concepts going on here, so we will get some practice with the common ion effect as well. So the solubility of a salt in pure water is higher than its solubility in an NaCl solution. So I would have less precipitate. I'll just put PPT, and I'll put more soluble, because I have to remember less precipitate means more soluble. Silver chloride produces less precipitate and therefore is more soluble in water than it is in a sodium chloride solution. So this produces more precipitate and is less soluble. And that's because it has that common ion. In this case, the common ion is the Cl-1, okay? Silver chloride and sodium chloride both have that chloride ion. Therefore, we say that that is the common ion between them. And that's what we have to look for when we do these examples, is what is the common ion? We have to identify that first, and then we can go ahead and work through the problem. So let's try sample problem 20. Consider the equation. I have the dissociation of cadmium sulfide here. The KSP is 1 times 10 to the negative 28th. If I place a small amount of cadmium sulfide in a 0.010 molar solution of cadmium bromide, what is the molar solubility of cadmium sulfide? So we have to first write an equation out. The question is asking us, what is the molar solubility of CDS, of cadmium sulfide? Molar solubility is what is the moles of cadmium sulfide that dissolves in 1 liter of solution. Okay, this is what I'm looking for. So how many moles? I really should put the question mark up there. And it is asking for cadmium sulfide. So I'm going to write my equilibrium or my equation out as cadmium sulfide. So this dissociates into cadmium ions and sulfide ions. What is my common ion? So I'm considering 2 solutions here. I'm placing a little bit of cadmium sulfide in a 0.010 molar solution of cadmium bromide. So clearly my common ion, I'll just put Ci, is the cadmium ion. And I'm going to try to draw a picture to show you what this is representing. So it's saying I have a solution, and in here I have the 0.010 molar solution of cadmium bromide, and I have a pipette, and I'm going to add a little bit of cadmium sulfide. That's the cadmium sulfide here. Okay, so I'm starting off with the 0.01 molar cadmium bromide. And I want to know, how is that affecting the solubility of cadmium sulfide because of that common ion? I should know that I should precipitate more cadmium sulfide because my cadmium bromide already has a higher concentration of cadmium ions in it. So guess what? Got to set up an ice chart, right? When in doubt, ice chart it up. This is a solid, so you don't have to worry about that. My initial concentration of cadmium is this 0.01. This is my common ion, 0.010 molar. And I have no sulfide present because I'm placing a small amount of cadmium sulfide in this 0.010 molar solution. So that's my initial concentration, but that contains the cadmium ions. It does not contain any sulfide ions. Then I'm adding some cadmium sulfide. Right? So because I'm adding some cadmium sulfide, I know that I am going to increase my amount of cadmium, and I'm going to increase my amount of sulfide, right? I don't know how much I'm adding though, because it does just say a small amount. So I'll just put here small amount. We don't know what it is. And my equilibrium concentrations would be 0.01 molar plus X and X. So I want to know how many moles of cadmium sulfide is dissolving in 1 liter of solution. So I have my KSP, right? And I could figure out what X is equal to, right? Because if I know my concentration of sulfide, I know that that's equal to the concentration of cadmium sulfide, which I can then use to figure out how many moles, which then gives me my answer. Anyway, let's set up an expression. KSP is equal to concentration of cadmium ions times concentration of sulfide ions. I know a lot of these values already. So my value for KSP is 1 times 10 to the negative 28th. Very, very low. And that's equal to this value right here. Now here's a very good thing. Because my value for K is so small, right? And this is true for any time you do a problem like this. Because this value is so small, the concentration that this is changing is really not affected, right? So if we were to actually determine, and by leaving this in, right, what's the value for X, you're going to get some number, but that number is going to be so small with significant figures, it's not even going to change this, right? So what we can do is we can do what's known as neglect the X, right? So I'm going to take this and I'm just going to get rid of it, that plus X part. So I'm going to say neglect the X. And that's because the value for KSP is so low. So we don't even have to consider that in our expression. So I'm going to take 0.010 molar times X. Look how easy that makes this calculation. If you did that minus X in there, you would get a number that is so close to the number you would get anyway. So ultimately it doesn't matter. Don't make more work for yourself, right? Chemists are logical sometimes, or they do make work easier sometimes. Not all the time, but sometimes they do. If I solve for X, I would find that my solubility is 1 times 10 to the negative 26th molar. If I consider, right, what does this mean? So this is my concentration of sulfide ions, technically. That's my molar concentration of that. But because this is a 1-to-1 mole ratio, 1 mole of sulfide ions is produced from 1 mole of cadmium ions. This also means that this is my concentration of cadmium sulfide, which means that I would produce 1.0 times 10 to the 20, or I would dissolve 1 times 10 to the negative 26 moles of cadmium sulfide in 1 liter of solution. This is my molar solubility right here. So that's how you would determine your molar solubility. Just like one of the other problems that we did in the last video, if the question did ask you for what is the solubility in units of grams per liter, you would just convert that from moles of cadmium sulfide to grams of cadmium sulfide. Let's try this last one here. So what is the molar solubility of calcium oxalate in 0.15 molar calcium chloride? So same thing, if we draw a picture out here, I'm starting off with a solution of 0.15 molar calcium chloride, and I'm adding some calcium oxalate to that. So this is my CaC2O4. And I want to know, how is that changing the solubility of calcium oxalate? So it said, compare this molar solubility with that found in sample problem 17 for pure water. So we're going to compare the molar solubility in pure water to the molar solubility in this new solution, right? And we're going to say, well, how does the molar solubility compare? Is calcium oxalate less soluble in this common ion solution? So my common ion is the calcium. Ci is equal to calcium ion. And I do want to know what is the molar solubility of calcium oxalate. So I'm going to write my equation out for this. I don't know what the heck that was. Calcium oxalate It's in equilibrium with calcium ions and oxalate ions. ICE, don't got to worry about that. My initial concentration of calcium is 0.15 because I'm starting off with this and I have no oxalate present. My change is plus X and plus X. So I get 0.15 plus X and X. I'm given my value for KSP. KSP for calcium oxalate is 2.3 times 10 to the negative 9th. So my KSP is equal to this times this. This is nice because I really don't have any squares or anything to consider. So relatively easy problem. 2.3 times 10 to the negative 9th. Again, I can neglect that X, and that's because my value for K is so small, it's not really going to affect that initial concentration too much. So I'm just going to keep my calcium concentration to 0.15, and I'm going to set that equal to X. And when I find that, I get 1.5 times 10 to the negative 8th molar. And you can compare these two, because if you were to subtract 1.8 times 10 to the negative 8th from 1.5, you would still, or 0.15, you would still get 0.15. This is why we can neglect that X, is because it's not going to change that concentration nearly enough. So there is my concentration in this particular solution. Let's compare. So with the common ion, my concentration of calcium oxalate, I would have 1.1 or 1.5 times 10 to the negative 8th moles of calcium oxalate dissolve in 1 liter of solution. In pure H2O, so I know that my molar solubility is 4.8 times 10 to the negative 5th. We determined that in sample problem 15. So 4.8 times 10 to the negative 5th moles of calcium oxalate dissolves in 1 liter of solution in pure water. Just compare those number of moles. I could dissolve a lot more moles. My dissociation is much higher here because I could dissolve more moles. 4.8 times 10 to the negative 5th is much higher than 1.5 times 10 to the negative 8th. So by adding that common ion, by having those calcium ions present in that solution, that is decreasing the solubility of cadmium oxalate, which is promoting precipitation. So again, because I am dissolving 1.5 times 10 to the negative 8th moles of calcium oxalate, I'm dissolving much less in the common ion solution than I am in the pure water solution. And this is why we say that these particular types of problems, these common ions, promote precipitation. Okay, that addition of that common ion, we can produce a heck of a lot more solid there because I am increasing the concentration of one of those products. As always, if you have any questions, let me know. We will work with this in class, so don't fret. But otherwise, we are done with equilibrium. There's a couple more things in that CED that we haven't done yet. One of those I think we'll talk about in the acid-base unit. And then the last one we're going to talk about in Unit 9, actually. So for me, we are done with equilibrium. If you have any questions, let me know. Otherwise, I will see you in the next unit, which is all about acids and bases. So I will see you then. Bye.